Okay, can folks online hear us okay?
Yep, sounds good.
All right, thank you.
So I'll give you a brief introduction.
Yeah. Let's make it fun.
So welcome everybody to Howard Shiz, MSR, that is Master of Science in Robotics, thesis presentation, final presentation. Howard joined the lab 2 years ago. He's been working on India Autonomous Challenge stuff, not just during the time that he's been here, but prior to that when he was at San Diego, the University of California, San Diego. And he's done a lot of work on that, some of which we'll be talking about today. And also has been involved with some recent interesting projects along with Vanya Shur, who's on the committee. Thanks also to Simon for being part of the committee, for those of you who are attending. So that'll turn over to Howard.
Thank you, John.
Where's that suit? Shouldn't have jacket.
It's cool.
Okay.
All right, so I'm presenting my thesis today on optimal control and robot learning methods in Agile safety critical systems. And specifically, we're using autonomous race cars as an example to infusing some of the robot learning paradigms into optimal control problems. And sort of an overview of what I'm going through in today's talk. First, I'm going to state some of the motivations about the whole autonomous racing challenge. And then we'll move on to see the two methods that's included in this thesis, which number one is our spline-based optimization method used as a optimization tool for initializing some of these learning problems. And then eventually we'll propose area learning model predicted controller, which is a novel learning MPC technique that takes a look at the data and then basically figure out a better approximation of the robot dynamics as it goes to explore these unknown regions, and then maintain a notion of safety, and then eventually learn, number one, what's the optimal control policy, and number two, what's the optimal local dynamics of the vehicle at different operating conditions. And we'll conclude some of that with how this would help us eventually think about what we would call foundational control models.
Do you want to be going to the presentation?
I think I'm already in. I just don't know how to full screen it.
It's weird.
Yeah.
It's supposed to be full screen.
How do you do that?
Oh, there's a right click. There's option enter full screen. No, I just saw that.
The three dots.
Three dots. Okay.
Three dots in there.
This one.
Yeah.
All right.
It's much better.
Yeah. Okay. Oof. I've never figured out that part. Okay, so and then I think before we dive into these kind of techniques, I want to sort of review on some of the crossover literatures with doing learning-driven controls. And very specifically, I want to identify three kind of strategic resources that people generally utilize to perform generalizable or learning-based control methods. Number one is what you would call offline knowledge. So this would include simulation data or your real training data from the previous runs with your robot. And then those are knowledge that are number one, they are widely available. You can go through them. There's no time constraints. You can go over them and then train models or do whatever things you want on them. But also there's issues with them in the sense that number one, you might have sim to real gaps. Number two, you might have data with the robot that was it was a robot with a slightly different dynamics, even if it's real world data. And the second class of resources is what we call experience. So this is as you are running the data, you gather a list of runtime data of your robot's states and controls, and that's compared to offline knowledge, this has been happening much more closer to the present time of your control. And then there's might be some useful information out of that, and this is where we would see traditional adaptive control coming to place. The third kind of resources is your online computation or online compute resources. So this is if you're using an MPC, you have the ability to utilize your CPU to solve for symbols, constraints, limits. And then if you're using something like MPPI, you get a lot of the power from the GPU to do parallel rollouts. And these are sort of the three resources that if you use them wisely, you can see some like very interesting crossover work in learning-based controls. And also one thing to point out is like when we talk about online computation, I'm not talking about, for example, using like deep neural nets to just infer like a policy you train with RL. I think that's like that's just simple inference. It's not like you are using some of the compute to actually do adaptations. And if we draw like a diagram representation just to show like where of the previous literatures are, and these are the traditional kind of techniques that you would generally see. So starting with the bottom right, you have the optimal controls. That's the MPCs and PPIs. They use a lot of online computation. MPCs especially generally does not really leverage any of the offline data that you have gathered. With experience, we're talking about adaptive controls, ADRCs, L1s, that takes a look at of your previous robot state for like a couple seconds or minutes, and then you do some kind of learning of the robot dynamics based on that. And then offline knowledge, this is where a lot of deep learning and reinforcement learning methods are. And in the crossover sections, you see some of the previous works. With on the left, adaptive control plus some of the RL-DL techniques. We have a couple interesting works. Number one is rapid motor adaptation, or RMA, which basically use some of the simulator knowledge about the environment to do open loop adaptation in the real world with adaptive control. And then also NeuroFly, which trains a dynamic deep learning network. And then you also use adaptive control technique to do some of the online adaptations. On the right, you have the crossover between optimal control and some of the learning techniques. For example, TD-MPC is a representation of that using both MPPI and also RL-driven techniques. And on the bottom is where a big part of our today's topic is going to be about. We're leveraging optimal control plus some of the adaptive control techniques in our error learning MPC formulation. And specifically, we're using data of the robots that's being driven in our current experiment, and then do some of the learning or dynamic approximation based on this. And finally, there's a little star reserved in the middle that we'll talk about in the end about what that means or how that's fit into the future. So the next section, I'll be discussing about the applications of this research with this, which is the autonomous racing challenge. And also feel free to interrupt me during any of this presentations. So this is a video of our own vehicles driving on Panama road course in Indiana. This is running tracking MPC with a speed up to I think 140 miles an hour on the straightaways. And this is sort of the just the standard approach using MPC to do racings or drive a car. You have a highly nonlinear vehicle dynamics model that you use some DEP technique to linearize them at every time step. And then eventually you solve like a QP problem online. And that's the car we go. And some more knowledge about the racing that we're dealing with. We are part of the India Autonomous Challenge. It's an international competition where you run full-size race cars up to 200 miles an hour. It's a competition. It's a software-oriented competition. You get the same hardware for every team. There's no. It's not like the Formula Student series where people have to design their own cars. And then also there's also head-to-head aspect, which is although not part of this thesis, but also something to think about is the multi-agent interaction aspect of the competition. And we have a lot of people in the game, including CMU and also Berkeley. Why is control a hard problem in racing? And specifically, I want to make a distinction between hard and unsolved. So hard means like this is things that just people are dealing with right now. Part about number one hard problem is you have very complicated dynamics. So you have race car tires that are notoriously known to degrade over time online, and then that introduces a time variant dynamics, for example. And then you have many things that are very stochastic and very, very unknown to you at runtime, including aerodynamics and also even like the temperature of the track changes that could have a very significant effect on the car's handling and friction. So those are the hard problem. And also we have safety requirements. You want the algorithms to be as real time as possible, and you want to build very solid engineering. Most of the current SOTA solutions.
How's yours?
Sorry, is that a question online? Okay, all right.
So you probably should ask everyone.
Okay, if everyone can mute themselves, that will be great. Thank you. So the current SOTA solutions in this domain usually includes MPC variants in the real world, and then you see some of the reinforcement learning methods in the simulations and small scale experiments. And I think one of the big reasons that people generally haven't been exploring these things on reinforcement learning based methods on full-size race cars is considerations about safeties, and but people are generally catching up. But so far, all the MPC-based variants, you have SQB-based convex MPC, which is what we run, and then you have robust and adaptive MPC formulations as well that people use to deal with some of these time-varying dynamics.
So regarding aerodynamics, how large is what is the air drag coefficient for ND? Just curious. Let's raise something.
What coefficients?
Air drag coefficient, CP.
Air drag, it's configurable. I think it's like if you go for just a speed configuration, right? You want to get the most speed possible, you can like knock it down to like 0.9, something like that.
But we cannot ignore this.
Right, exactly. Aerodynamics play a big part. Like it's not just drag, but also it's about downforces, right? Like so, if you have more downforce, and then your tire sticks more to the ground, and then
so it's part of the model, part of that model.
Right, exactly. It's part of the. It's also part of the nominal model.
Oh, it's
yeah, but like nominal model is like it's not accurate. Right? It's just like a quadratic drag model, and that's pretty much it. And we don't have a full understanding of like the full aerodynamics effects. Like otherwise we would be an AA student. So robotics people. Moving on, why is control unsolved in this whole scenario? Well, number one, we haven't found a great way of effectively basically adapting model and policies.
That's not done, but like, I guess I can get some results like this afternoon.
Cool. If you want to do presentation, there's like
I'm gonna. Right, cool.
Maybe you can send a chat, like if you don't have questions, please.
Yeah, doing that right now. Okay, a bit awkward, but let's continue. Okay, talking about control is unsolved. Number one, you have data that you want to leverage. Just remember that the Venn diagram we're just showing, you want to leverage them in different ways. They're coming from offline, they're coming from when you're running the car, they're coming from like right now with your compute. And then also multi-agent interaction is something that really hasn't been considered. And some of our research directions, learning MPC, that's the one we'll be talking about. And also potentially into the future, we want to do some adaptation with neural MPC methods. So just a summary of the motivations for these methods in autonomous racing. Number one, you're dealing with a real-world multi-agent and high-speed racing problem. It remains unsolved, and it sounds very fun problem, but really like autonomous racing is about deploying robo learning in the most wild situation possible. And then also you're considering a lot of these real-world safety critical constraints, and it's on a safety critical platform. So the next section will be presenting our last year's work, mostly on what we call the spline-based optimizations. It's a fast racing trajectory optimization problem that we can formulate with minimum prior. That means we do not rely on any of the previous robot dynamics. And then the whole hope is that this platform will basically take you from zero understanding of your vehicle dynamics or any robot dynamics in general to like the full mastering of it, like after you run through the whole learning MPC pipeline. So with Spline-Opt, this is the initial stage where you are just like getting started with your robot, and then you want to try to find something that makes the most sense and then is the safest way possible. So the specific challenges with this stage of autonomous racing is you have this chicken and egg problem. Number one, you want to go high speed. But you want to go high speed, you've got to have a good dynamics model. But if you want to do that, you need to go to high speed in the first place to basically collect some of those data and then regress back a good model for And then sometimes this is not doable. Sometimes, like, for example, human expert data is not always feasible in a setup, especially with our race car, since the cockpit is completely filled with electronics. And there's so little data that we can use to verify these vehicle dynamics. And also you always want some like offline method, since you know the racetrack beforehand. Using like offline method like these optimizations would help with online problem a lot. And then people can generate afterwards just like run like a sampling based planner to get around obstacles and then come back to optimal race line whenever possible. The goal of this work is we want to investigate a predictive optimization problem using splines. And then there's a couple requirements. Number one, we want to use the minimum vehicle dynamics data, which means we're not formulating it just yet as a optimal control problem. And then number two, we want to guarantee the trajectory smoothness up to at least C2 continuity. This means the robot can position is C2 continuous, and then you get also in your control loop, you can expect smooth control commands. Number three, we want to produce a fully parameterized trajectory. This means we're not doing discretizations in the problem decision variables. We're just simply using splines to represent the trajectory. And number four, we want to reduce the problem dimension with SOTA method. So with previous work in HANS racing, what people generally do is you just segment the track into like 10,000 pieces, and then you do like OCP based on that. And number one, it's a big problem dimension. And number two, it makes it impossible to run online, which our method can also turn out actually to be an interesting online global planner. And so that D&E there is really just about having a small problem space as possible so that we can also do this optimization online. And the figure on the right is like an example of visualization of the program's output. So initially, the most rudimentary data you can give into optimization is just the blue line in the middle, which is the center line of a track. And then you have the gray boundaries also given to the program. And then in the end, it optimizes what we call minimum curvature trajectory that's suitable for autonomous racing. That's in orange. So some backgrounds. This is a little bit mathematical part. We're using B-spline in this paper. So what are B-splines? You can think about them as a combination of what we call basis functions. That's visualized on the right here. These basis functions are recursively defined. So you can see, for example, here when you have order 2 B-spline, these are really just triangles. And then you perform a linear combination of those triangles, you get like a smoother and smoother basis functions when you go higher and higher degrees. But of course, like when you go higher and higher degree, like you can start to parameterize like even more arbitrary complicated curves, and then that might become arbitrarily unnecessary. So like in the end, you don't need a trajectory that runs around in circles in like really curvy shapes. So we choose like a third order degree B-spline, which is usable. And one thing to note on the bottom here is when you're parameterizing a 2D curve like this, you would have basically two sets of one-dimensional B-splines. So the T is goes from 0 to 1 is the parameterization of the curve. And then these are what we call the control points. So if you've known some of the geometry tools on your computer, you would probably know some of these tools like Basel curves or B-spline tools that gives you like little points in your program to drag around, and then that alters the shape of your curve. And this control point Z is the same idea. It's the coordinate of those control knobs or points. And that's actually the decision variable of the optimization problem. So basically, we're strategically placing these control points such that the output trajectory would constitute some sort of notion of like optimal trajectory. And this is a visualization of the famous turn at well, doesn't look so famous on the picture, but looks like it's a Monza turn 1. Turn 1 at Monza track in Italy. And this is like an example of what the control points would look like to parameterize this center line, which is shown in blue here in the middle. And these red points constitute those control points. And then if you move around those knobs, you can imagine this blue line would also like shift here and there ever so often. And the goal of the program is simply to optimize that. So here's the optimization problem formulation. Number one, we're minimizing the total curvature of the line. This is what we call minimum curvature racing line. And this is usually the racing line that you would choose to if you have basically zero understanding about your vehicle dynamics. And then the actual minimum time racing line, which is like all we care in racing problem, is actually usually tend to be very close to the minimum curvature racing line, but just because of the vehicle dynamics, some of the linearities in that, it tends to differ from it. If you have vehicles that can corner very specifically good, or it can go on a straight line, accelerate very specifically good, then you would like optimize it further a little bit more, and that becomes a full OCP problem. So that's the goal of the minimization, is to simply minimize the total curvature of the track. Then that is constrained by some of the track boundaries, and talk about in the slides about how to formulate this lower bound, upper bound for the track boundary. So it's like you're looking at your left, you're looking at your right, and you try to find the track boundaries. The decision variables is the point placement of the control knobs. And then we're expressing curvature here first as a nonlinear function. And we'll talk about how to make it QP solvable later on. This is the general formulation of how you would compute the curvature of any kind of spline or any kind of curve in math representation. And in the end, this is where you would we would use B spline as a function of the decision variables.
Yeah. Two quick questions.
Yeah.
First, why minimum curvature? Shouldn't we care about like V square kappa if we want to optimize centrifugal force, right? It's fine to have small curvature, but with low speed, right?
Yeah, that's a good question. So think so the end goal of like this a specific Spline-Opt is so that we can solve it in the QP as well. And then generally, if you want to solve minimum time problem, it's a nonlinear optimization.
No, I mean like something like coupling curvature and speed.
Oh, I see what you're
I
saying.
think the motivation.
Yeah, that's yeah.
I think the motivation of minimum curvature is you want to reduce the centrifugal force, right? You don't want to roll over the vehicle, and also you want to make it fast.
Right.
But that should also be related to speed of the vehicle.
Yeah, exactly. Interesting you should say that, because like we actually do some of that experiments, and we find there's like a little paradox. So the paradox goes like this, right? So if you use like if you put like velocity also in the cost function,
Yeah.
so what it's meaning that you're caring less about the curvatures at a point where there's like less velocity.
Yeah, it's what I
right, and then
then
you care more about when it's on. And yeah, and then we tried that, right, and then we figure out that like what's happening is then like the cars, it's like the track optimization is just like caring, like unless you tune it very right, otherwise like it doesn't care about the cornering so much. And then cornering is actually, and like later on when we run the optimization with an actual minimum time problem, we find out that cornering is actually pretty important. And it's actually the place that will cost you more time, because like if you don't optimize your performance in the corner, then you're gonna like come up on the straightaways like slower than the other people, and then we also try the other way, right? Like maybe we want to weigh more about those points in the corners versus on the straightaways. And in the end, I don't think like that produced like consistent results on like different kind of tracks with different kind of geometries.
Yeah, I guess the intuition is because the car is super low base, you don't need to worry about rollover. It can basically whatever curvature speed. That makes sense.
Yeah, exactly.
The other question is, once you get spline, how do you ensure it is feasible? Like possible? Like is there some differential planets that are going on? Like, so how do we know like the car can actually track this jack route?
I think that's one thing that is actually not so much considered because of two reasons. Number one, we're on the racetrack, so we know that racetracks are designed for race cars to drive through. And then number two, it's what we call the minimum curvature optimization. So like we are already basically the only case where the car cannot traverse through a trajectory, right, is where the curvatures go so much that even like a kinematic model of the car can't really turn that turn, right? But since we're already doing this optimization for minimum curvature, and we know that the track is probably traversable by like a vehicle since it's a racetrack, and then we sort of ignore that constraint just from that.
Cool. Thanks.
Yeah. Talk about that. Okay. So on the next slide, we'll talk about a little bit how to get this track boundary constraint and do so in a linear way. So if you represent your z's, right, these are x and y coordinates. They are in the global frame, and then if you try to express things in a global frame, you get some nonlinearities with the whatever heading you are, and then you're decomposing your positions and try to look for the track boundaries on your left, on your right. And so to get around that, we use a local freenet frame approximation. So what's happening is we are converting the global x and y representation of the car, and then transition and basically rotate it into the local freenet frame, so that we get a nice number of basically the distance to the left of the car and distance to the right of the car as the track boundaries. And also we want to approximate this problem as a QP, and the reason is later on we want to also potentially convert it into an online planning problem. And then the way we do that is basically by number one, we can take like a little SQP based kind of assumption that the first order derivative of the spline does not change throughout, which is it's an approximation for sure, but like it's reasonable approximation that the general direction of the trajectory would remain somewhat unchanged here in the middle. And even if you are worried about that, you can take like SQP approach and then do subsequent iterations of optimization problems, and with a new update on the first order derivative of the spline. So with that, the most nonlinear part is just about the curvature, and then with that assumption, we can form this these matrices in this way, such that these terms on the matrices represent either the second or the first order derivatives of the spline, and then now you get a QP problem in this nice form, and you can just solve in one QP iteration. And it will return you the optimal placement of these spline control points that will form the best trajectory possible. And also you get options later on to do SQP and then do iterations after that if you're not satisfied with your approximation. Here are some of the results. So a bit of explanation of what's happening. So eventually, usually, first of all, we're feeding the algorithm with the center line of the track, and that's shown in blue here, dotted in the middle. And that's the input. And then we do a parameterization of that with B-splines, and those end up with these original control points, which are these blue points along the track that is shown here. So these blue points represents the B-spline parameterization of the center line. And then in the end, what's happening in the optimization is like you see these little arrows here that shows basically where they were before and where they are afterwards. And then in the end, the placement of these orange, which are optimized points, form what we call the minimum curvature optimal race line. And here just more results on like a different section of the track. I think this is model that turn 7 and turn 8. And also what we're showing here on the right graph is a comparison with the previous work. So I think here it's like interesting to note that a lot of these things we're doing, like we're not trying to get like a trajectory with an even shorter time than what's the current SOTA method, right? Like that's bounded by what your vehicle performance is. That's not bounded by the online planning stage. What we're really trying to get is basically represent the same optimization problem with much less decision variables, and then still maintain a similar level of performance.
Yeah. This blue is trying to solve a full time optimal control problem.
It's trying to solve, yeah, it's trying to solve basically a full nonlinear optimization, not time optimal, but still with like curvature optimal. Yeah.
Which is way slower than.
Yeah, exactly. So that's what we're comparing on the next slides is the table on the left is meant to show that you get so finally we run these lines with our simulators and with vehicle dynamics, and then run them on them and basically show what's the best speed possible. And then what we want to see is basically we want to see very small changes in all these delta between our method compared to like a full discrete optimization problem. And then we've showed that works in most of the parameters. If not, well, the minimum speed is a little bit off. I mean, this is percentage, this is not absolute number. We show that we are doing this with a much smaller parameter decision variable space, be able to basically achieve the same level of optimality. And with the previous work, you get basically just the number of decision variables is just how long your track is. And then with spline interpolations, you can knock that down to just the placement of the control point. So that's a much smaller copy problem. And that reduces the solve time from basically seconds to like millisecond range, which is now usable as an online global planning method.
So these numbers are from planning or from closed loop result, you use MPC to track this stuff?
The time, yes.
I mean, this the lab time.
Yeah, the simulation, yeah, it's from MPCs.
Oh, is it closed loop?
Yeah, it's closed loop.
Nice.
So yeah, and here are some high-level comparisons of our method against what's the current SOTA using discrete methods. Number one, in terms of smoothness, we output a fully parameterized trajectory that is guaranteed to be at least C2 continuous or higher if you want to choose to go for higher order B-spline. Versus discrete methods have no guarantees on that. And number two, yeah, it's fully continuous, but then it's only discrete waypoints outputs, and then we have a low dimensionality on your problem space. And then also this potentially enables us to deploy this as like an online global planner later. So some takeaways from the spline optimization method we're just discussing. Number one, we've proposed a spline-based optimization method which has smoothness guarantees, can be used on both online and offline, and requires basically low dynamics data. And then the constituents of this method, of course, is number one, we don't consider dynamics, but like we will talk about why it's useful to our use case. And number two, it's sensitive to some of the curvature and spline degree tunings. Like we've chosen degree of 3 just because we know that like cars tend to not jerk too much, then like over orders of like 2s of B splines. And then the second thing is it's not the true minimum time optimality, right? Like that requires like a full OCP problem to be solved. Because we'll move on. So now we've seen this spline optimization, and then you've seen the output of it, which is like a trajectory that is sort of optimal. It's minimum curvature. It's very close to what the optimal time trajectory is that you will need to traverse through the track. But how do we actually achieve that optimality, right? So now we are like 50 or 30% in the middle, right? Like before this optimization, you have zero knowledge of your vehicle dynamics. And now you are in the second stage where you sort of have a good trajectory that you can track, but you still have very little understanding of your vehicle dynamics in general. And that with that, we'll move on to the next stage of the work, which is the error learning model predictor controller. And this is the online running stage where we would run the car on the track and then let it figure out on its own what's the best dynamics model for it at different speeds, and also what's the best control policy for it to achieve that optimal trajectory. Here we show that it's a similar motivation as the spline optimization problem. You're still dealing with the chicken and egg problem. You still want to basically enable this gradual exploration of your vehicle's dynamics and then over iterations. And that's like one of the available methods to get you out of this chicken and egg problem of requiring dynamics data in the first place for you to go to that dynamics range. And we show that by basically number one, start with a non-expert demo, and that could be the outputs of the last stage of the spline-based optimizations. And then eventually we iteratively improve and then find what's the optimal model of the vehicle and also what's the optimal policy. So some previous works specifically in racing domain. The goal is always to basically learn and adapt to system modeling era. And then you have a bunch of popular approach, and then a lot of them are actually based on Gaussian process. So you use Gaussian process to fit these vehicle dynamics data, and then they work reasonably well. And, works cited here, I saw the citation numbers, but the work cited here is from Francesco Borelli's lab with using Gaussian process to actually not only predict your vehicle's own dynamics, but also the dynamics of the opponent agents. Gaussian process has like underlying Gaussian assumption, but it doesn't leverage necessarily the iterative nature of the task we're dealing with, which is racing. You're racing in a loop, like you're racing in iterations. There's a lot we can leverage just based on that. And then one of the most classic example would probably be iterative learning control, ILC. That also takes the same idea. So if you're doing a task over and over time, you can sort of find like regularities in your previous iterations of this task, and then try to exploit that. Yeah.
Can you go back?
Yeah.
So I remember like the paper 7, Google's paper, it that doing it. I remember it doesn't learn dynamics, right? It learns the
Right, exactly.
terminal value function from MPC.
Yeah, exactly. So with the traditional learning MPC formulation, you're not learning dynamics, you're just learning the policy.
Okay, I see.
Yeah.
So you want to.
Yeah, exactly. We want to have a framework that does.
Okay, so like just to make it clear, like 6 is only learning dynamics, but
Mhm.
not learning policy. 7 is only learning policy, not learning dynamics.
Yeah, exactly.
Okay, cool.
And this is a pipeline of how like a normal learning MPC formulation would be. So you start with basically non-expert data. This is your initial data set of your vehicle's states, and then the correlated control variables in between states. And then when you start an iteration, you start to basically from the environment record all these data of the vehicle into a data set. And this is the same as your initial data, just the vehicle state and all the controls. And then somehow the learning MPC policy is basically querying from this data set, right? Like what's the we'll show this in the next slide coming up. Basically, what's the data that makes most sense for it to for the learning MPC policy to learn the optimal policy, and then in the end it outputs control to the agent, and then at the end of the iteration it basically appends this big data set to the end of this whole giant data set that's maintaining in the background, and then the process just continues until you find the optimal policy. And we'll talk about what's the learning MPC policy in the next. So one important notion with whole learning MPC and with just the way it's dealing with safety guarantees is using this idea of a sampled safe set. So what is sample safe set? Well, to put it in the easiest way, it's really just the set of all the states of your vehicle in your previous iterations. So what's nice about those data is that it is guaranteed that, you know, as long as your robot is in any of those previous states, and as long as the environment doesn't change, you always have the guarantee to go back to what we call the terminal state, which is the state that you go past the start finish line. So the reason is this, right? Since you've already done, like in all these previous iterations, your robot has already all successfully completed all of the task it's asked to do, which is drive a full lap on the track. And you know that as long as you're in these states, as long as the environment doesn't change, you can always follow the same sequence of control commands, which will take you back to the start finish line again. And that is why we call this set has controlling variant properties. And the terminal set is just defined as all the points, all the states of your vehicle that is beyond the start finish line. So this is then will become the formulation of the original learning MPC. So it's like I can explain line by line, but like I think what's most important is really just the bottom constraint, and all the rest are like very nominal in the MPC formulation. So you have optimal control problem that goes up to some horizon. You have dynamic constraints. You have dynamic constraints. You have initial state constraints. You have primal bounds for your optimization variables, and then in the end, you also constrain such that you want the robot to always return to the safe set at the end of your horizon. So here we're dealing with we can deal with arbitrary nonlinear functions in your dynamics. But the original learning MPC formulation also causes a problem. So because this is a discrete set, right? This is a set of all points. Maybe there's 1,000 points in here, but they don't really form like a nice space for you to do optimization problem over. This is very discrete. So if you try to basically just directly constrain that you must end up in the safe set, it becomes a mixed integer optimization problem, right? Like you need to actually look at every individual of these points in your safe set, and then that's what the optimization problem is going to do to be able to find what's the optimal safe set to return to. So to get around some of that, and then to have a nice space that we can do optimization problem over, we use the idea of a convex safe set. So this is a convex combination of all the previous states of your sampled safe sets. And then the convex combination is noted here with the parameter alphas. So as long as it's a nominal combination, if you don't limit that, they must sum up to 1 and must be greater than or equal to 0. And then, but with that, it's a what we call convex optimization. Sorry, a convex safe set. Oops. And you can prove that with guarantees that if you have actually an LTI system in the form of AX plus BU, convex safe set actually also guarantees safety throughout all combinations of the points in the safe set. And also, if you're solving a learning MPC with a linear LTI dynamics, is also guaranteed that all the points, not just the last point, but also all the points in the horizon are also going to be guaranteed to be in the convex safe set. But that's only a nice property you have with linear systems. And with nonlinear systems, this generally fails, but also we want to exploit some of these properties using some linear approximation techniques. So a summary of the classical learning MPC problem you just seen. Number one, it only considers a linear system. If you want to have a nice problem, you can do optimization over at runtime. And number two, there's no dynamics learning just yet. And then number three, it doesn't really leverage the data set efficiently, right? Like we're talking about a convex combination of basically all the points in the data set, which goes up to thousands. And that becomes some of the motivation of our work. We want to, number one, also learn dynamics in the learning MPC formulation. And also number two, we want to work with, even if you have like very little data set, you still want to form like a convex set like this. And also when you have too much data from the previous iterations, we want to find what's the best data in this scenario. And also we show later on deployments of these methods in full-size race cars. And here is the full formulation of the error learning MPC. So we consider MPC with a nominal dynamics model, which is x equal to f of x and u. This is number one, nonlinear, and number two could contain some kind of modeling errors. And another thing to explain is in the cost function, you have number one, your nominal MPC stage costs, which include penalties on controls and control rates. And the new thing to add here for the learning MPC would be this Q term. So what Q term is doing is that it's in the end incentivizing the MPC to basically reach states that is further and further down the road. And this represents the whole like time optimal behavior for the MPC. So this cost function here basically uses so if the state was recorded, for example, like 1 meter away from the start finish line, then it's associated with a certain cost that is different from a state that was recorded like 2 or 3 or 4 meter away from the start finish line. And in the end, the MPC through this cost function is motivated to basically find the state that is associated with the least cost associated in this Q function. And then that incentivizes MPC to find basically the state that is further ahead possible. And then over iterations, that becomes a optimal time behavior for the MPC. Also, some of the techniques that is not noted here is number one, we want to learn a local approximation of the dynamics, and we'll talk about that in the next slide. And number two, we will also use a convex hull to relax the safety set constraint. This is the full problem, so like we still know it as SS here, but in when we're deploying it, we would replace that with a convex safe set. The stasis, so the quick note on the state space model of the vehicle, we're using single track dynamics, and then we're expressing our pose in the FreeNet frame. So this includes 2D velocities and then also the 2D poses. And the aerodynamic regression goes as follows. So you consider number one, a nonlinear system with also an error term, which we call E of x and u. And then you use Tyler expansion to get a local approximation of what that error is. So A and B and C are the linearizations of the error terms, and then the x and x and x hat are basically your prediction against what was actually reported in the data set. And then the A and B and C does the local linear approximation of the errors. And then in the end, you can stack all of these differences in your x and x hats together, and then you can stack them to make a regression problem. And that's expressed here. So all of these equations, what we do is you're simply stacking together all the states. And then also there's a kernel function here that basically deals with the weighing or scalings of the states that's in the data set by saying that all those data that is outside of this kernel's bandwidth, I'm going to ignore those. They have nothing to do with my local dynamics. And then as you get closer to the center of the kernel, which is the current state of the vehicle, like they are generally weighted more in the distribution for the regression problem. And in the end, you come up with these terms in the A and B and C matrices, and then you stack them and then add them back to the original linear model of your AX plus BU. And then you get a local linear approximation of the entire error dynamics. So you have the linear approximation of your nominal model, which is coming from f of x and u, and you have the linear approximation of your error dynamic, which is coming from regressions. And here's where we're showing the results. So we compared number one, which we'll call a full regression. That is like the most vanilla way of doing error dynamics learning is you just stack all the matrices together and then you solve a least square problem and then call it a day. Versus us with using number one nominal model as a prior, and also number two regressing different dynamics terms separately. And the y-axis here you're seeing is the lap time reductions, and then the x-axis represent the number of laps. So we do 20 lap experiments in the simulation. And these lines of different colors here are with different tunings. So one of the main motivation for us is we want to deploy Learn-MPC actually on a robot. And then we're deploying things actually on the robot. It makes a lot of difference that you have something that is robust against like different parameter tunings versus something that you just have to find a sweet spot in order for it to work. And with the race car, you don't get a lot of trial errors. And then we want you want to start with parameters that might even be less optimal, but is still able to at least make the lap. And that's what we're showing here. So we're showing different tunings in what we call in the control rate costs. And control rate cost is something that you can think about as governing the learning rate of the MPC, right? Because if you limit the robot to vary its command a little bit less, then it's going to basically learn, stick closer to the original safe set at every iteration. Versus if you allow the robot to do very aggressive behaviors in the change of its controls, it's going to stay farther away from the safe set, as far away as allowed to, as long as it go back to the safe set in the end. So with a higher penalty, that's CLC equal to 1.0, that's the graph you're showing on the top. That's the slowest rate of learning. And then we sweep that through across multiple magnitudes, and then in the end, all the way to 0.01. And we can still show that the residual learning is actually working compared to if you use a vanilla way of doing this, it would just simply start to fail. So how is the robot actually, what's the progress of the robot's learning? So these graphs here shows there with simulation experiments, so we have perfect understanding of what the vehicle dynamics should be, and then we can actually start to quantify some of the errors. The green line on the top graph shows the magnitude of the actual model mismatch in the dynamics A matrix. So that's basically the baseline, right? So if you want to learn something, you want to learn something that could make the model mismatch less than that. And then the red and blue again once represents our error dynamics learning, and then with a full dynamics learning, and then we can show that both methods are learning. They are eventually achieving to the same level of optimal, but because of the fact that just using vanilla regression would simply fail, like most, I think half of the blue lines doesn't even make it to. And the next slide shows the experiments on the scale hardware, and we'll have videos on the next slide too. But here's a visualization of the learning progress of the vehicle. So on the left, you have the lap at the first iteration. So the original data given to the car is simply a tracking MPC running on the center line of the track for 3 laps, and that forms the initial data set of the vehicle. And we believe this to be basically readily available if you even transfer this method to some other platform, not cars, but also other forms of robots. you can always use some like nominal controls, even PIDs, to get you that like initial non-expressed data. And we give that, and then this also in the first iteration, it's learning to basically cut some corners in those in the most curvy areas. I think I need to plug in battery. Computer. Sorry, 1 second. Yeah. All right, cool. Apologize for that. So you have the first iteration on the left that's showing some improvements, although like not so much improvement over the overall speed of the vehicle. And then in the middle, you have the fifth iteration. That's after 5 laps. So you can see it's already pretty good at finding what's optimal way of cornering, and also trying to get it gets up to speed every iteration. And then in the end, at the 20th iteration, you have the robot in the most optimal behavior of cornering. And then you have also that's like basically maximizing all the speeds around the entire track.
Quick question: Can it learn that its model generalize to new track? This is a local model. What's your prediction track? Suppose you're doing another track.
Yeah, if you go to a different track, you need to end up basically starting from your non-expert data again.
Right.
Yeah, because like I think
I got that you could make sure that
right.
You get to go to a new track after the converted here. Will that happen?
We didn't try, but I would imagine a big issue with that would be like, for example, there's maybe like location dependent data that we are overfitting. It's like whole linear learning pipeline.
So it's probably better from scratch.
Yeah, probably better from scratch. So here are videos of those scare hardware experiments. Just so. So this is with full dynamic repression, and then start with some in the beginning. So this is driving on the center line, and then it starts to learn a little bit of cornering, like really always fun. And that's mostly the nominal learning physics. But in the end, what's interesting is that after a couple laps, it starts around. I can see it like a while in the front. And then this is with the aerodynamic regression. I can skip the initial portion. So, so of course, after scaled hardware, we want to deploy on the real world, and we did. So this is the full-size testings at Putnam Road course at Indianapolis, and this is a test track for the Indy Auto Challenge. And this is the trajectory recordings of the full-size Indy cars running this same optimization problem and optimized on this little test track that we have provided. And then what's zooming in here is the vehicle's performance in this chicane here at turn 1. And you can see some of these low speed data that is clustered closer to the center line of the track, which it was given as the initial non-expert data. And then over iterations, you see the robot basically cornering and better, and then get closer and closer eventually to the track boundaries. And it doesn't fully overlap with the track boundary because the vehicle still have a width. Consider that. And also like it learns to corner at a higher end. And finally, this is video that one. And skip. So here, this is the same track that you were just seeing on the graph. The initial data was collected with the just running MPC on the graph. Yeah, so this is the initial data collection. We run a tracking MPC on just the central line of the car with like constant speed, very low speed. And then here, this is after 5 laps. So you can see that the vehicle is already like start to learn some of the race line aspects and then try to corner the most optimal way possible. And after 10 laps, it's finding it optimal. I know it looks slow on the video. It's actually pretty much at the limit of.
Where's the waveform from? Like from the slide. Optimization stuff we usually
I think for this experiment, we want to show like the most unbiased results possible. So like we like basically we did not give it any like optimal reference, like even from the spline trajectory.
How about the indoor?
Like saying like we're showing like the unbiased results. So yeah, so if you that's the pipeline we're going to be introduced with. If you're feeding the one from the offline optimization, it's of course like going to start way better than what we, and you can even like just start to do a tracking MPC on the optimal race line, right, and then collect the data and then just start from there. And I think that's probably like what you would go for if you want to learn it the fastest way. But careful research, like we're just giving it the center line of track. So, yes, so that is from basically looking at all the dynamics data that we have on hands available, our understanding of the vehicle, like also similar cars with Indy cars, like, and also looking at the curvature of the trajectory is trying to track, like we think that's the highest speed, like possible way to do it. I think this is a very tight turn. So I think we're looking at a lateral G of like 1.5 G, like 15 meters per second squared. Yeah, something close to that. And then, yeah, and these race car have like perfect tires, 1.2 on the news, but yeah, like 1.5 G is pretty much also you would see the limits of these individualized cars in other cities. Of course, like Formula cars would go higher than 3 or 4 Gs. Okay, so summaries from the error learning MPC. So what we presented here is number one, a simple machine learning method. It's not deep. There's no deep learning method. It's a machine learning technique for dynamic learning using residual learning. And then what's happening is you start from zero understanding of the vehicle dynamics data, and then eventually you go on and iteratively explore the tasks that you have on hand. And then you, in the end, learn number one, what's the optimal dynamics, and also number two, what's the optimal way of handling the vehicle. And in this process, the vehicle is learning both the dynamics model and also the control policy. Some of the limits of this method. Number one, you are always like basically limited by this expressiveness of the local linear dynamics approximation. So it comes with all kinds of problems. Number one, as Brad just pointed out, if you go to a new track, it's going to fail because like you're learning the local linear model. You're not learning the global landscape model of the full range of the dynamics. And number two, it cannot handle basically non-iterative cases. And this is a task that is specifically designed where we can exploit this repetitive nature of the task. And in the end, this will be the pipeline for the entire explorations that we do with autonomous racing. You would first run some offline optimization, assuming that you have zero understanding of the vehicle dynamics. You can run the Spline-Opt to get this initial coverage optimal reference. And then you can run some MPC on that and then form an initial data set, which will eventually be passed down to the error learning MPC to do the optimization. And then in the end, you have this optimal policy and also good understanding of your robot activities. So at the end, this is the closing sections that we talk about some of our current work and also like just directions coming from these learning MPC approaches that we might call a foundational control model. So a recap with error learning MPC in this bigger picture diagram utilizing all control resources possible to you at runtime. I think this star in the middle is the next area that we tend to explore, and you might call that foundational control models. And what that means is that you have a control model that can adapts to controlling unseen robots within the current class of robots. So we're not talking about adapting to, for the same model to adapt to all kinds of robots, but we're talking about with some specialization, you can adapt to controlling robots that you have no idea about what the next will be. And I think some of the learning MPC or most of these learning-driven control techniques give us motivation to build these generalizable control policies. and also dynamics learning framework. And also some of the motivation comes from people doing these large language model or foundation model for planning for robotics, is they want to have like a low-level control policy that can also handle ambiguities, right? If you're talking about a manipulator that is manipulating objects with different masses, and then people on the high level generally does not want to care about like what your controller is going to react to, as long as it does the right thing. And then even if you are lifting different masses or doing things like that, like you want to have a robust control model. And how generalist should a generalist be? That's a good question. And you can have this pyramid of controllers that is like specialized in all kinds of degrees. With towards the top, you have those methods that is not so much adaptable and very specific. And then those that researchers like spend one night or several nights tuning the parameters just to get things to work. Those are probably too narrow for us. And also too general, we don't want the car to control, we don't want the policy to control all kinds of robots we have on hand. We wanted to have the right amount of specialization so that it can, number one, learn efficiently, and also number two, master the specific dynamics efficiently. And that's where we might pursue some of our future work in generalist control models, but also with specializations. So you're talking about a class of controlling a class of robots, regardless of their sizes or optimal performances or whatsoever. So this can be a car, a small F-110 car with a big race car, a car on the moon, a car on the Mars. That's interesting generalization we want to see. And you can see some of these previous work by other people. Some popular ones, many quadrupeds, where people learn robust policies that doesn't really adapt. And then, but in the end, they can still control robots of different sizes, from little doggies to big dinosaurs, using the same basically regularized control policy as robust. And also, I mean, we have Neurofly that's doing some of the adaptive controls, but also in the reactive control sort of way. And then we see basically in these class of methods, you're using deep learning to train dynamics for your robots, and then and exploit some of the structures in the dynamics models, such that you can do very rapid online adaptations to account for different or changing dynamic environments. So I want to close this talk by some of the takeaways about our current research towards foundational control models. Number one, we want to leverage structures in neural network designs, and we want to enable efficient adaptation to do few shot or zero shots controlling of unseen robots. So with that, thank you everyone. And I want to thank my thesis committee here and also my collaborators and the faculty advisors at UC Berkeley, and also wonderful labs that I have a time to work with here at CMU. So thank you so much.
Okay, so
okay.
I guess we will, after we go out
yeah.
I think we'll,
okay. I guess. Oh, sorry, but I guess are you going to be audible on Zoom? I haven't been using any of this. I know.
Well, I guess you could
Repeat the question. Okay, yeah.
Yeah, so about Spline-Opt. So what do you anticipate?
The benefit of, I see. So the question is, what's the benefit of online synthesis of race lines using methods like Spline-Opt? I think so. Even if we're doing a global trajectory optimization, there's still online aspects that you want to replan over when you're online. So so what this could be include as an example. Number one, actually like this is less general, but like just with dealing with race rules we have on hand. People generally form race rules that like places like static obstacles on the track that you need to like replan over. But like more generally, like if in the end like you find out that even if you're doing global optimization, there are specific areas on the track that you don't necessarily want to step into or have like very poor dynamics. Like this could include tracks that have like very different surface coefficients in these different areas, or just general race rules like that forbids you from like driving into certain areas that you haven't anticipated in your offline planning stage. And then you also need to do some of these plannings. And also not also just like global trajectory planning, but also you can use the same spline method for like local plannings to get around other vehicles. I think those are possible future work we have.
So in the case of dynamic obstacles, why would you do dynamic
well, well, with strategy, you're also doing planning, right? Like you're doing planning, and in the end, you want to find like a trajectory that goes around the obstacles. You can do that with solving like a nonlinear optimization problem with your dynamics like in mind. Of course, you can do that. It probably takes some like much longer time. And then simply like using, for example, QP problem with like splines, and also you can achieve like the same level of behavior, right? Like you can give it like like boundaries for the planning as like a tube to go around the vehicle, and then you can solve for an optimal way around.
Okay. Yeah. So have you compared this? Are you aware of models like design model? Any method that you
Any method using hand design cornering models? I talk about like dynamics function, like people use like dynamic functions specifically designed for like vehicle in cornering compared to going on straight lines.
Yeah.
I'm actually not aware of. Okay.
Okay. One up.
Yeah, it's good work.
Thank you.
I read about the filter, the diagram.
The diagram,
Yeah,
this one.
the-
Oh, okay. This one.
No,
Oh.
the first slide, the
Oh, the Venn diagram.
right in the middle.
Okay. Yes.
Yeah. So, like, question like the first, like for the first part, like the slide ends. Are you aware of the minimum snap framework for photography?
The minimum.
Minimum snap for generation. I feel it's very similar. Like it's basically they try to minimum snap. Snap is the first order derivative position, kind of related to curvature. Like you don't want a drone will have big snap.
Right.
Then like they basically do QP formulations, like you solve with kind of as a very good surrogate of all optimal computing. The reason why I'm bringing it up is if you can argue it's a general framework first, and second, the theoretical foundation you can do that for drone is a difficult class system. So it can track any smooth polynomial trajectory, same as the vehicle. So the best model is difficult flat as well. So I actually encourage you to think about this direction. So actually you can say something about it's even though you ignore dynamics, when you plan this plan, you can still argue something from different planets. Kind of perspective.
I see.
That'll be interesting. They're also related to where's the star, right? Like you said, like specialization, right? I'm understanding the specialization related to how general this physics abstraction is. Like different planets is also very good angle to think about, right? If you can argue this framework works for any physics system that can use this abstraction, right? Okay. And the second question is very philosophical. Is so since like everything present today follows the this separation principle in control. You first learn the next model. When you learn the model, you basically don't care about what is the downstream policy, what is it, whether or not you do then you do MPC, assuming the learning model is accurate, this is actually constantly equivalent, right? If you equivalent to that one.
Yeah.
So the question I want to ask you is, are you going to continue working on this kind of paradigm, or do you think we should go beyond that, like coupling dynamics learning and policy learning? Do you think it's necessary to achieve the start there, right? Because you can argue that the main like limitation and the separate principle is you don't have to learn perfect models to have good performance, right? Is exactly what some cost data for that. Right? Is the clear answer?
Yeah, I think
Can you summarize?
I'm sorry. It's a yeah.
I meant wrong.
I think it probably. I'm going to speak for
Maybe.
but yeah, I think you're nodding now. I'm seeing the mic symbol, so that's probably good. Okay. So yeah, I think, for example, the error learning PC, like I think already gives like an example of like you don't need to care about like a simple model that can capture the entire domain of operation for your robot, right? Like we're all just doing things locally, right? Like we're looking at where you are right now, and then we fetch some data of the robot around you, and then we form this local linear problem, and then you do that for wherever you go, and then this means like you don't really need to understand like what's the actual dynamics for the vehicle, but you just can simply just do local approximations and then get your matrices in your local linear model terms. And I think there's also ongoing work where people do dynamics in the more implicit or latent space, and I think with that is probably where people would see the argument that you don't necessarily need to have a model that is a ground truth, but you want to have a model that's more suitable for your controls, or like a couple problems with your controls. And like my feeling is that like with probably like more traditional state-space representation of the robots, I think that gives people a lot of motivation for you to like basically be able to knock down things to where they actually are. Because like you're looking at things in the explicit state space, and then you would have a very good sense if something is not working. Versus if you're taking things into some latent space, then I represent your dynamics in there, and then like number one, like I think there's very little thing you can do to actually verify that your dynamics is actually making actually accurate in those kind of spaces. And the only way to tell if there's a good quality model or not in those kind of situations is by basically looking at a close look control performance. So, I think I want to explore some of that. So I want to explore, for example, TD-MPC. I think is a very good example of the work that I admire recently, and just like things that leverages deep learning techniques and then do things in the latent space and then represent the dynamics in there, and then hopefully that enables us to control more complicated robots and also be as generalized as possible.
Okay, thanks, Mike. I have a couple questions. So let's see, when you got done with the Spline-Opt part, you mentioned that you haven't really taken into account the errors there's. So my question is, do you have, I'm kind of interested to know how much you would have to modify something from the Spline-Opt using the weighted approach. It seemed like you're starting with center line. Did you try any experiments with taking the output of the Spline-Opt and then seeing how much it needed to be modified?
I see. That's actually a good question that we haven't explored. Yeah, I mean, it's going to improve the learning performance, but yeah, like the question of like back to looking at how close that the initial spline learning actually is. Yeah, we haven't looked at that, but that would be interesting.
I just wondered if it's good enough, right?
Right.
If it's good enough for certain cases, then you're going to have to bring in the report. Wondered about. The second question is with the sample state set. It seemed like maybe, probably not to say it right, but there was potential contradiction or issue in that if you craft, you sample certain states, but then your model is changing changing and things in the environment. Now, when you look back at the sample state set, it's not, as you said, really safe when the environment's changed. Does that create any problems with that at all?
Yeah, exactly. So, okay, so the question is about like what happens if the environment changes, right? So if the environment changes, like would learning piece methods still work? And I think that's actually ongoing research at Raleigh. So and you can see obviously from this formulation, like this definitely relies on the fact that like number one, it's iterative paths, and number two, the environment doesn't change. Or doesn't change that rapidly, right? So these paradigms would still work if you have like environment that's slowly changing in the sense that you can still capture some of the changes in your like previous 2 or 3 iterations of data, right? And then and also you can include weighings just based on like how recent data was sampled. Yeah, exactly. That's actually something we do. Like when we're querying, like we're only querying data set to ask for like the previous like 10 iterations of data. And then if you have like any dynamics that are changing faster than that, then probably it's hard to know.
Okay. Last question is kind of detailed, but on slide 40. Maybe 40.
40?
Yeah. So is it the case? It seems like the first lap has a significantly different lap time for all of these. Is that just because the error learning rate makes that big a difference in even the first lap? Because otherwise, I think the first lap is about the same time, and then it would go down to all of them.
Yeah. So initially, I think the point on the top would probably corresponds to basically because like the data was coming from tracking MPC, right? The tracking MPC running at very slow, like 1 meter per second, just doodling down the middle of the track.
Right.
And I think that's probably going to be represented by the first lap of this highest term here. And yeah, I think even the first lap, like I think the first lab is really where like the most drastic change happened, because like this centerline reference is not really optimal in any sort of sense. So like the learning NPCs tend to like do very very well on the first lab to optimize it, and then try to cut corners on centerline. Okay. And also like centerlines have like very high curvatures in some reason, like especially with chicanes. And so like if you have a horizon that's long enough to know that at the end you're gonna have to you don't need to really follow the center line to go through the chicane, then it can already know how to knock it.
Okay. All right. Any questions from the audience?
Yeah. Go ahead.
Yeah, can include online.
Oh, people are going on. Okay. That's a very good question. Yeah, certainly in this work we're mixing everything together. Like in the initial pipeline, like all the initial data is really collected offline. It could be the robot driving in the real world, although we haven't tried robot driving in a simulator. And then we just take that on and then just take it for granted and just use it in the online formulation as well. And yeah, I think this structure that does not consider, I guess, like separating simulator knowledge against like real world knowledge. I guess I don't see where it can fit in just yet, but I guess that would probably be like separate paradigm. But I think that's interesting on like different platforms.
Your last chance to get out of hard. Maybe.
And good talk. So how did you get down to other robots, like it?
That's what we want to figure out.
Yeah. Any thoughts? Outside you have to modify, like see this diagram to make it work for like a robot.
Yeah, I think too much we just take the smooth dynamics of the vehicles for granted. Yeah, that's going to be probably the toughest thing that we need to deal with. Is like you probably need to start working with the data set so that you can classify different like contact modes, like store them somehow separately in the data set. Yeah, you need some hard.
But I think it's like when people who work on something like this could do that. Nobody.
I think we can Nobody online?
Nobody online, yeah.
We can probably wrap it up.
Okay.